One of the first few things I made when I was trying out Uiua was Conway's game of life. And as you can see, it's kind of like really odd looking code. And not only that, but Uiua's been a developing language ever since I started it, like started picking it up. So most of this right now is like deprecated, right? So this doesn't work anymore. So I thought to myself, why not revisit how I would like write this now that I'm much more experienced with Uiua. And well, for the uninitiated, it's Conway's Game of Life. So the cellular automata or automaton, and it's one of the most popular, right? And basically how it goes is you have like cells, tapos you can put dots when wherever as your starting condition, and then yeah, just like that. And but every like cycle or every period, there will be rules that are enforced to determine what happens to your cells that you like wrote down. So rule one is any live cell with fewer than two live neighbors dies. Two or three live neighbors lives on to the next generation. Three live neighbors dies. Then exactly three live neighbors becomes alive. So if you pay, like, if you like notice the pattern here, it's actually you just have to check neighbors. So there's actually a pattern here for the conditions. All you have to check is the neighbors of every cell in your current life, and then you can use that to determine which cell survives or gets gets created for the next cycle. And it's an end gate between every single cell that has two live neighbors, and then every cell, and then it gets ORed with every three neighbors cells. This the middle one has two live neighbors, so it should stay, and then also the side. So this will actually oscillate, right? Because the ones on the sides will the ones on the sides, these guys, okay, they have three neighbors, so they exist. No, any dead cell with three live neighbors becomes a live cell, so it becomes like that. These guys on the side, okay, they die because they only have one live neighbor, so that's why it oscillates. So let's go about making that. So a feature in Uiua that I've been wanting to understand more is the fact that it can output images, right? It can output images, and how that goes is if you give it like a really big two-dimensional arrays, okay, it interprets it actually as images, as pixels. Every element of your matrix will be a pixel, and then it's a value ranging from like 0 to 1, 0 being black, and then 1 being white, and then the rest, like if you want color, okay, you're gonna be replacing those elements with tuples of RGB. That's really all that you need to know. So if we have, say, range, we duplicate this first one, so we have 50. Then we divide everything by 50. No, we flip this first. And then we divide it by 50. That means we have a range from 0 to 100 because it's numbers 1 over 50, like n over 50, right? So it's 0 over 50, 1 over 50. So now we have these values. Now if we turn this into a table, like we table it on kind of equal, this would give us an identity matrix. Like if we at this we have a massive matrix with ones to the main diagonal. So if we actually do a less than equal, it will get this matrix wherein everything on the bottom left is a one. And if we look at the image output of this, it would be like this thing. It's a slash, and that's nice. So we can actually use that to parse images, right? So what I'll put this back. Since we have a matrix here, and then it just parses ones and zeros as like black and white, all we really need for game of life to work, okay, we need cells that are like ones and zeros, alive or dead. So that means we just have to make the normal game of life code, and then it parses it to an image immediately. And moreover, if you have a three-dimensional array of matrices, you can consider them as frames. Then you can generate get and GIFs. So if we have this, and we do a row rotate on fix uh, 1, then 2, 3, 4, 5. You can see it's actually rotating it. Now if we do a range here, like up to 50, okay, we have this weird pattern now. So that's cool. It's rotating upwards. So yeah, so we're gonna be using that. So we'll be generating an initial state with like randomization, and then we'd want to get the next state using like the rules of Game of Life, and then we'll want to keep all of those in a single array so that we can use them as a GIF. First and foremost, let's do the random start. So let's create a 50 by 50 na zeros. So right now we have a one-dimensional or an array, an array of zeros, and then we want these to be 50. So we just do a where 50. We flip this, so we have 50 at the top of the stack, and then if we call reshape on this, I will get that. So it's already a matrix. We can do %s to print this. So right now we have a 50 by 50 zeros, and we will verify that by checking its shape. It's 50 by 50. So nice. Now for the randomization, we actually have this function called random, where it gives you a random number from 0 to 1 exclusive. And if we do that for each element, then we just replace, or like we pop off the value and then replace it with a random. We'll get static. So that's cool. And if every time I run this, it'll be different. It's random. Now, if we want to like lower the density of the white, okay, we can multiply this by a factor. So let's do it with 0.6. It's less now, and then we'll round it, and that should make it much more sparse. The reason we're doing 0.6 here is because if we do 0.5, that will always be less than 5, which means it rounds down. But if we 0.6, it's just enough so that some of them will get rounded up. So this is our initial. And if we print initial here, okay, we get that. So one thing you might notice is this is a very tiny image. And you'd be right, it's quite tiny. So the next thing we'll do is we upscale. So how do we upscale matrices? So let's comment this out right now. So say we have a matrix of 1, 0, 1, 0, 1, 0, 1, 0. So that would be like this X pattern. And then if we turn this into an image, we force it, it's just 3 by 3 pixel width. So we want like squares of these ones, right? Like himona to siya na ang every one will become like a 3 by 3, and every 0 will become a 3 by 3. That's upscaling. So how we do that is we give it a factor we want it to upscale by. So let's say we want to upscale it by like we want to turn every pixel into 10 by 10. So we put our 10 here. Then if we do a double over here, it just duplicates the top 2 of our stack in order. That's nice. The reason we're doing that is actually we should probably flip here. The reason we're flipping here is so that it maintains its order like this, right? So if we get the length, or like how many rows this has, okay, we can get 3. Then if we turn this 3, if we turn this 10 into 3 of those shape, we get 10, and then we do a what's it called, keep on 10 10. So that would make it so that every row here will be duplicated 10 times. If we do keep, now we have 10 of every row, right? 10 of that, 10 of that. Then if we do a transpose, okay, this should give us our normal array, our original array, except all of the numbers are stretched to the, like, how do you call this, horizontally by 10. And that means all that's left to do now is to do it again, but these guys as our like cells, right? So we want these guys to be duplicated horizontally again and then transposed, so that means they will be duplicated downwards, and this is our square now scaling. So that would be like the same thing again, and then length, tapos just keep reshape. That it's much bigger now. That's cool. So you might notice that this is actually repeated code, right? And that means we can just wrap it in the repeat, and then we do it twice, repeat 2. That's much terser. And now we have this leftover 10 from our solving, and can't really do anything about that except we do a dip, which means it temporarily pops this matrix we have, and then we do a pop, which is semicolon. We do a dip pop, so it removes this temporarily. So when we do a pop, okay, it removes 10, and then it puts back our matrix. So that's clean. So if we up this value, we up turn it to 100, we upscale our image, and this is very nice. We can use this to upscale our initial. So if we turn this into a function, upscale, I upscale, and then we remove this. Tapos we generalize our factor. Okay, we just leave it like that. If we do upscale 5 initial, we will have this. Then if we do upscale 25, okay, well, a much bigger image. So that's nice. So a very important part here is that we have an upscale, but we shouldn't upscale this, our image first before we do our game of life rules. That's because if you recall, okay, what this would look like, it's just can't even print it. Every cell now has like adjacent na of like the upscale na to every pixel, which means if you interpret this with the game of life rules on 9K, it's gonna be messed up. It's gonna be like wala ni mo na upscale ang imong game of life. You upscaled the cells and then you did game of life. So let's do that later. But we have an upscale function now. So we have initial. So now we need to figure out how to apply the game of life rules. So let's start with the little one. So let's do initial na 3. So it's a 3 by 3. Okay. Actually, let's do a 5 by 5. Okay, that's nice. So how do we get neighbors? So first, okay, I've done this on a previous video, I believe. I just check rotations. You apply rotations sa imong array. So how that would go is you do a range na 3 by 3. This would give us this array, multi-radix, kanang 0, 1, 2, 0, 1, 2, 0, 1, 2, and then 0, 0, 0, 1, 1, 1, 2, 2, 2, 2. So if we subtract 1 to this is actually our rotations that we want to do. Then if we rerank 1, this is rotate up and then rotate right, and then this is rotate down and rotate up and then don't rotate. And then if we apply all of these rotations, no, that's how that would look like. We need to fix this. So our rows function would know na i-apply na to siya to this entire array. If we do that, rotate. Sorry, rotate. And then we'll have an array of all of our rotations from our original from our original array. These are rotations there. And then if we do a folding sum on this, I will get its array, or like its combination, or like neighbor niya na mask. And that's because every rotation, pag overlap sila, they will have a 1. And then if you add them, okay, it increases. So the cell 3 has, this means na iyang original array. If we copy this, we'll see it clearer. So if we look at this cell here, it says here na it has 3 neighbors, and you can see it right. So like 1 here, 1 here, then 1 here. Then if you look at here, it has 3 neighbors. That works. So if we go here, okay, it's a currently existing cell. So it will have a 1 on it because of the 0 rotation, and then it has another 1 because of its nearby cell. So we want to get rid of that. We want to not count cells themselves. We only want to count neighbors. And how we do that is we actually keep the cell, this matrix of our original, and we just subtract it because if they have a 1 here, we subtract it from this, okay? This would actually remove the effect of the no rotation matrix. Actually, it's comma, so that's an over. So this will put it in the front. Then when we subtract, okay, that would give us the actual answer. If we look at our on this one, okay, it says it has 2 neighbors, which is correct. Then if we look at this one, it says it has 1 neighbor, which is from the top or the other side. Which now we have that. That's good. So moving on, we just need to apply the conditions that we figured out earlier, which is that we just need a map on all of the 2s and the 3s. So how that would go is we do I believe 2 and a 3. So it will have a 3 and a 2 sa matching nila. Then we can use this to do both equality. We'll check, or like we'll get the masks of kung asa ang ilahang mga matches. And then if we do an AND gate of this 2 na mask over the original, and then we do an OR gate with this one, okay, we get our next na cycle. That's good. So we do a dip na minimum, and if you can think of it this way, a minimum sa 0 and 1 is just the same as AND gate, right? Because if you have a minimum sa 0 0, that would be 0, minimum sa 0 1, that would be 0, minimum sa 1 1 would be 1. So you can use min as a substitute for and the function. So we have that. It says here it's 0. And then if we do a max afterward, okay, that would be our AND gate, our OR gate. And then this would be our next cycle. So if we look at this, we duplicate, okay, it says here kanang 1 and then 1. So this means this guy should be alive if it's already alive, which isn't true. Now this one it has a neighbor of 1 here, 1 here, and then 1 here because it wraps. That means it has 3 neighbors, so it should be alive the next cycle. So that's correct. So if we do a 25, this is much bigger, a lot of numbers. And then, so let's delete this. And then, again, then this would be our like life function. So on initial, we need to do a fork identity fix. We need to provide this like a starting size, so 25 by 25. So the reason we're doing a fork fix here is so that when we join something to this guy, it'll treat it as like an array. Right? So like if mag-join ta og another matrix to this, it will join it as a frame. To make sense here. If we do a repeat, tapos let's say this would be our number of frames. So if we say we repeat this 50 times, okay, what would we want to do inside here? So you'd want to do is on the top one sa stack, okay, we want to apply life because right now it has a copy initial and then a fixed na version, or basically ang array na tong i-keep track ang atong frames. So sa top sa stack, okay, we want to do live, and then we want to join it with the fixed na version. Tapos we want to like basically repeat the cycle. So we'll do a fork identity. That way we'll have like a new copy na pod. So on the right, okay, we'll have the frames we currently have, and then we join then this one fork ID. Okay, this would give us our next na cells, and as you can see, these are frames, right? Nakalista sila, and then we have an extra one here sa ending, and then we just want to get rid of that. And that would be like a pop, I believe. So it's truncated here, but there are 50 of these. And then if we do a GIF S, then we give it the number of frames per second. Okay, this should give us this image, and it's quite tiny right now. That's why we have an upscale function. So if we do a row upscale, okay, we should upscale every row, and then we want to give it a value of the factor. So we upscale it by 10, it's this big. So now, if you may notice, okay, this is moving quite oddly, and that's because our frames right now are reversed because we were prepending. I actually have to do a reverse here sa ending. And now we have life. Isn't that nice? If we turn this faster, I believe this can go up to like 45 before it starts screen tearing. It's pretty fast. So 50 frames goes by really quick. So let's turn it into 250. Yeah. So this goes by too fast. So to appreciate. So let's turn it down to like, I don't know, 12 frames per second. Yeah, we have life. You have a glider here. Oh, it's gone. So if we upscale our initial, it'll take a bit longer now because again we are brute forcing this. So not actually sure if this finishes. Oh, it does. So now we can just admire this. Absolutely beautiful. All in 4 lines of code.